Again, okay, time is up. So, good morning, everyone. Thanks for coming. So, it's a great pleasure to have our four distinguished speakers here. And today we will have, actually, we will have 2 days presentations. So, on the first day, we will have two keynote speakers today, and tomorrow we'll have another two. So, first of all, I would like to just welcome our four distinguished speakers. The first one is the James Townsend from Indiana University. And the second speaker would be the Mario Fifish from Grand Valley State University. And Ami Idos from University of Newcastle. And Joe Haupt from University of Texas at San Antonio. So actually, we have such kind of meeting 10 years ago. That would be the first time that Jim came to Taiwan. So this is his second time here. So it's a great pleasure that Jim can come here twice. So Professor Townsend graduated from Stanford University a long time ago, and he's the expert at the mathematical psychology and cognitive psychology, and he's a leading expert in our field, and he serves as many great important positions in our mathematical psychology society. And he has published a lot of things, and I think he will, in today's talk, he will give you a very brief and easy way to understand the general recognition theory and the assistance vector technology. So I don't want to waste time, so just join me to welcome Professor Townsend.
Thank you very much. Okay. I'd like to express my gratitude to Professor Yang for getting this group together. And last time, I think, so this is kind of an anniversary, and last time I think it provided kind of a nucleus for a rather amazing amount of research that Jing-Ta and my younger colleagues here, all of whom are my students, I have to claim, are former students. Now they're teaching me things. So anyway, it's a wonderful thing, and I really have a lot of gratitude to Jing-Ta for bringing this about. It's an amazing chance, and we're looking forward not only to spreading the word with you folks and the people in Taipei, but also finding some time to discuss and contemplate some of the deeper issues in our field, both these kind of what we call meta theories, as well as deeper issues in the general field of mathematical psychology, which, like all fields, were still rather embryonic, having really begun in the 1950s and 60s. So it's really quite a young field. Of course, we have history with psychometrics and things that goes back into the 19th century, but the idea of using math like the physicists do to develop theories and then test them with data from the laboratory or society is a quite new thing. So it's pretty revolutionary, and I think Robert Heinlein actually mentions the field of mathematical psychology in one of his books. I can't remember with a Star Trooper or what, but didn't say much about it, but there you have it. So anyway, today we'll have what has to be a fairly brief tutorial, and I'll probably be repeating this in Taipei. So the experts here are going to get bored to death, but I can't help it. It's too bad, guys. So, but then we will move on to, I think will be of interest somewhat. I think they're somewhat familiar with the newer things, but to share also with you of some of the newer developments over the last decade or so. So with that in mind, we'll march forward. There's me, and there's in June, who was also my student. She's now on a postdoctoral fellowship at the University of Newcastle. I suppose, does she get to see you guys, once in a while in Newcastle?
Sure.
Cool. That's great. So here's where a lot of it started, as probably you guys are familiar that in the history that Gustav Fechner is accorded the status of being probably the first experimental psychologist formally defined by doing his work in psychophysics. He had a physics and philosophy background and thought he was solving that age-old problem, which is still alive and never die because it probably can't be solved, the so-called mind-body problem. So he's, and with the whole society, of course, devoted to his name and kind of work in psychophysics, called the International Society of Psychophysics, or simply the Fechner Society. This is a book that was kind of a foundation for a lot of what we'll be talking about today by my former student and myself, Greg Ashby, which we did on sabbatical that we had in Germany at Braunschweig way back in the, actually 1976. And I thought we'd get this book done in a couple of years, and lo and behold, it took another 6 or 7 years. This is a book that you might want to get into because it established all the new results up until that year, 2016 and 17, and Jim-NCKU was one of the editors. As you can see on that, Little, Altieri, and Fivich were also here back in the first edition of this workshop. And Dan, I guess, sustained an injury and wasn't able to, unfortunately, join us. But this has a lot of the applications in the whole fields, all the way from clinical psychology, psychophysics, and cognition. And here's a book that has just come out that I highly recommend, especially for those people that are interested in the history of psychology, experimental scientific psychology especially. And David Muir is a famous historian in psychology. And Stephen Wink was one of my comrades back in Stanford many years ago, and is also a major mathematical psychologist. And we were letting, this is a series that Stephen and I started long ago. And David was just doing all the work, but then we found out that, like almost all historians, he knew no mathematics. So once again, mathematics was being neglected in relating the history of psychology, which actually played a major role. Fechner, Weber, Herbar, on and on and on. And so Steve jumped into the fray here to help David fill in the gaps. So now there's a decent history, a very good history, in fact, of quantitative thinking in early psychology. And here's another new book that actually is my former student, Greg Ashby, is just finishing up now, but we'll hope to see in the next year or so. And it centers on statistical decision making, and especially signal detection theory, which the famous mathematical psychologist William K. Estes once said is probably the most important development both for experimental and mathematical psychology that has ever occurred so far. It's a big statement, but it could be true. Certainly signal detection theories all over the place. General recognition theory we'll be talking about a lot this morning, so I'll go into that more shortly. Let's shoot this in. Hard for me to see these things sometimes because I'm red, green, colorblind. I'll run up and point with my fingers about that. So, you know, all you guys are familiar with the idea of all the complexity, even in sometimes called simple perception, not to mention higher orders of cognition, and we're trying to explain. You all know that. Most of you have probably been introduced to this, but in the spirit of the tutorial, we'll go through it, the building blocks, some of the major mathematical building blocks that we use to prove theorems, make measurements of data, and so forth. So we have then the so-called cumulative distribution function. So the probability that a process has been finished at some time less than or equal to little t. The capital letters we generally use for a random variable. Those of you who have had some probability theory. Survivor function is just a complement of 1 minus the cumulative distribution function, and that's the probability that the event has not occurred by time t. Hazard function is a kind of micro level conception because it says what's the probability you'll make the event will occur or you'll make the response or whatever at time t given that you have not made it up until then. It's called a hazard function because it was first developed by the actuarial insurance people and that kind of thing. What's the probability you'll survive until, for example, 60 years old, given that you haven't died before then? And probability that a ship is going to make it to South America to pick up the stolen gold from the Indians, given that it hasn't met a hurricane so far, that kind of thing. And this is just the integrated hazard function, which integrates this up until some time t. And this h of t also has the property, and very interesting, that it can be thought of as a kind of like power or instantaneous work done at time t. It has that kind of dual feature of complexity. And the integrated hazard function, you can interpret it as the amount of work done up until time t. So very, very useful concepts. And Greg Ashby introduced the idea way back in the 70s of using these guys to as kind of building blocks to study mental capacity. Please feel free to ask questions too. So again, now we come to general recognition theory. And what it does, which is amazing, that ever since, well, Fechner actually used kind of signal detection theory, and Steve only claims that Fechner knew signal detection theory. Most of us take exception to that. He did use normal distributions and a criterion for making a decision which signal detection uses. But he always put the criterion right in the split middle where the two distributions of equal variance cross. So I don't think he really knew signal detection, but he certainly knew about making decisions in noisy situations. The engineers in the 1940s and 50s, including psychologists at the University of Michigan, collaborating, really good modern signal detection theory. And the physicists and engineers developed interpretations or even predictions that lead to some of the statistics. Moments, for example, mean and variance, as being functions of the actual energy in your physical environment. So, well, we'll see. So now let's start about looking at a tutorial kind of application signal of general recognition theory, where now we're generalizing signal detection theory to take into account more than one dimension. And thereby, in signal detection theory, there's one thing, like how bright is it, bright enough to be a signal there. Now we can look at different dimensions and how they interact. And that's the whole raison d'etre of general recognition theory. So suppose we're presenting stimuli that have the dimensions of color and shape. And here's an example of putting them together into a red triangle. For some visual features. Vertical line in the curve ending up as a English letter. Another example, and you don't want to think about these as all being within the same trial, they're very sensitive. These are different conditions you might have in 3 different kinds of experiments. So here you're simply, you've got different dimensions, but here you're only trying to look for the color, like a something blue. Here you're only trying to look for a particular shape, in this case a circle. And here you have a conjunction where you want the blue circle. So there's mixtures. Here's another blue object. Here are other circles, but this is what you're actually, that's the actual target. So I think people all over the experiments, probably video like this. Now here, this is really the critical part of the whole tutorial. And for general recognition theory, we stay in the upper half of this figure. So here are major kinds of what we can call dependence, but dependence used in different senses. Okay? We can also think of them as a kind of invariance, like we would in certain areas of physics. So here we have the theoretical properties, and we'll show some more pictures of this, but perceptual separability basically, let's explicate it by going through an example. If the color that you're given affects your perception of the shape, then that's a failure of perceptual separability. So if, making this up, but if the triangle makes the object appear more blue, that would be a failure of perceptual separability. If the shape triangle looks the same, and remember we're often talking about very weak para-threshold stimuli here, then you might have this dependence or you might not. If you do have that kind of independence, then that's perceptual separability. Let's jump down to perceptual independence because it's the most natural contrast with perceptual separability. Basically, perceptual independence refers to the way the dimensions may or may not interact in a single trial with a single stimulus. Okay. So if, say, your circle, the amount of circularity within a trial varies with your perception of the amount of the color, then that's a failure of perceptual independence. So, for example, if you have a plot like you're using the regression analysis of variance, and you have a positive correlation in the Gaussian distribution, then that would falsify perceptual independence. So again, that's a within trial thing for a single. Notice this is a cross stimulus. Varying an experimenter or reality, varying the other dimension affects this particular dimension, as opposed to what's going on within a trial with a single stimulus. Now, it turns out that decisional separability, though, is important too, just as people that were inventing signal detection found out that where you place the decision criterion is in some ways just as important as your difference between the means of the noise. They always call it noise alone versus signal plus noise, because their idea, the engineers and physicists' idea was that noise, whatever. So if you make the signal weak enough, that noise is going to affect stuff. Right? Well, if you put the criterion way down low, then you're going to catch the signals all the time, but you also make a lot of mistakes in the way of false alarms. You're going to say the target was there, or signal was there, well, it's not. Well, akin to that importance, it's even more important in a way in general recognition theory, because if you're decision bound for saying this thing is a triangle versus a circle, if that depends on the stimulus point in the space, you lose that decisional separability. And as we'll see in the pictures, try to remember all this in your mind, and then you'll see pictures to explicate or explain everything. Your boundary for same color, suppose color's on the X dimension and shape is on the Y dimension, then if you have decisional separability on color, your bound will be just a straight vertical line up and down from plus infinity to minus. That's decisional separability. It's very important because just as if you don't pay attention to the decision criterion, it can affect the way you interpret things in signal detection theory. That happens a lot more immediately and disastrously in general recognition theory. On the other hand, it's important and interesting, and Greg Ashby used GRT to develop a whole theory of categorization, which became very famous. And where you put your decision boundaries in making categorical decisions is turned out to be very, very important. Important part of those contributions. And we'll see about this stuff later on. Maybe we'll have to come back, we'll see, but I'd rather not go into it to mix up the concepts right now. We'll come back to the systems factorial technology. So now this just tries to explicate for budding mathematical psychologists by showing a little math to go along with my verbal statements that I'm working with. So perceptual separability, notice that we've got two different stimuli, so it's an across stimulus kind of thing. Notice the width is the same, but the length has changed. So if you have perceptual separability, your probability of seeing the horizontal one doesn't matter what the length is because these are equal probabilities, then you have perceptual separability. Okay. So this helps you build the math concepts that you use then in your thinking and theorizing and stuff. Next, we have perceptual independence. Remember that we claimed that that was a within stimulus kind of thing. It happens within a single trial. Same stimulus is the same. Probability you say this is the product of the probability that you get the vertical times the probability that you get the horizontal. There's a vertical and there's a horizontal. That's the same thing as what you learned in probability theory or statistics, what they ordinarily just call independence, or sometimes in more complicated model, they call it stochastic independence. It's a thing that happens on a certain trial. Again, stimulus stays constant, but is your perception of these two dimensions unchanged, or the product of the two instead of being needing conditional probabilities? And I think for decisional separability, I think the picture will help. So we'll get back to decisional separability momentarily, but we can interpret up until very recently all of signal detection theory, all of general recognition theory was basically from response frequencies, generally called accuracy and inaccuracy and probability of confusions and things like that. No reaction time in the original theory of methodology. So one thing we've noticed over the years is that general recognition theory using frequencies is extremely good at these various kinds of dependencies, but it's not so good at things like mental architecture, decisional stopping rule. And those is what we need systems factorial technology, or SFT, for. Well, now we have a nice picture to not completely, but partly summarize what we've been saying. So there's math behind all of this stuff that we'll just give them to you. And to get specific, there are actually tests that don't even depend upon the probability distributions, and unfortunately it's something you usually don't learn in elementary statistics. Elementary statistics usually assumes everything is normal or Gaussian. There are billions of things in nature that are not normal, are not Gaussian. Okay? Like if you want to study the maximum of the temperatures in a season in Taiwan, okay, that's never normally distributed, and it has different properties. If you take samples over and over again, looking at the maximum every year, and maybe look at the average of the maximum, that's never normal. And you have limit theorems that approach some other distribution that's not the central limit theorem, that's not normal. And yet too many psychologists say, oh, we got a whole bunch of things here, so it's got to be normal. It's not like, okay. But so our tests, that's why we made our tests here, and then in systems factorial technology, we made them largely non-parametric. They don't depend on particular distributions. However, if you say you pass the test of the non-parametric test, then you can go into a more specific model that assumes a particular distribution. And here we're using examples that are, in fact, normal distributions. These are so-called equal likelihood contours. So where these lines or curves are have equal probability. Now, we see here, this one's got bigger variance than this, but it looks like the covariance or correlations are about the same. And they're actually zero. You need the thing slanted like this or like this, negative correlation, positive correlation. None of that's happening here. So they're all independent in that perceptual independent concept. However, we see here the perceptual separability fails everywhere, basically. Here it fails actually by shifting the distributions as you change the stimuli. Okay, and these are even going to have different means as you change the other dimension. Here, you're not shifting the distributions. The means stay the same. That's a little off. It's supposed to be the same. This one is fairly the same. But the variances are the same. Well, that's still a violation because it's changed the distribution. So even though the means are the same, they're not the same distribution, so you're violating perceptual separability. Finally, the fact that your decision bounds are orthogonal here and aligned or parallel to the axes of the percepts means that you are satisfying decisional separability. That means that you make the decision about the y dimension, for example, looking here, without reference to whatever the other dimension is, just doesn't matter. So that's decisional separability. If you had like a line going like that, you would not have, you'd falsify decisional separability. It doesn't even have to be curved, it can be linear, but it's still violating. So now what's new? That's and hopefully the ingenues or neophytes, beginners, have learned something in the tutorial, but now we jump to something that hopefully will still be of interest, but to bring in the more expert people here, and some of them have even participated in the developments. But let's take a quick look at some of the developments over the last few years. So Townsend, Haupt, and Silbert, Dr. Silbert there, we developed to get ever more testing, ever more what we can call study, for example, electrical engineering, you can study systems identification. Well, all of this is bringing in mathematical tools and meta theories that are appropriate for psychology that wouldn't work in engineering, unless you're asking the same questions, and engineering stuff generally doesn't work because we don't have the same kind of dependent variables in things. Right? So like if the Martian comes to Earth and wants to find out the gain in what we might call an amplifier, they'll put a signal in here, out here, and measure the change in the voltage and all this kind of stuff. Unfortunately, we can almost never do that in psychology. So bringing in response time not only permits stronger tests of hypotheses, but encourages, and in some cases forces the consideration of deeper process models and project behavior. Now, we can begin to look at this, and what this does, of course, first of all, a lot of models that mimic each other, when you only have accuracy, all of a sudden they're identifiable or discriminable experimentally when you bring in the action response. So Greg Ashby was again one of the first to start to bring dynamics into neural recognition theory, and he was the lead author on our first paper on it. We have been, Michael Winger, another of our colleagues, have been working on using these kinds of dynamic systems because all of a sudden you can start to bring in control theory and all kinds of linear and nonlinear dynamics, which involve differential equations, stochastic differential equations. All of that becomes possible in your armamentarium to bring in the reaction time. And actually, we did these systems quite a lot in systems factorial, which we're going to go through momentarily. So it may look kind of complex at first, but they're actually pretty elementary when we understand them. So let's look at the bottom one and work up instead of top down like we usually do. So here's a model with two channels. Maybe one of these for color, maybe one of them is for shape. Okay? You got an input. These are the stimulus. This is like example a triangle, and this might be blue. Goes through this this is an integrator, and these are the simplest kind of dynamic systems, mainly linear dynamic systems. You go through, you integrate this material. You have typically, if it's a stable system, which means it doesn't go crazy, you send your plane down into like a couple of volumes. You send so-called negative feedback. That sounds bad, but negative is good here because it subtracts the input from the input and it goes around. This can create a so-called stable system. In fact, without it, you definitely don't have a stable system. Here's the output. Same thing for the other thing. Eta here represents noise, usually Gaussian or normally distributed noise. So you can take a normal distribution and make it dynamic across time, and you set certain things there. Still Gaussian, but it's not dynamic. So here's an interactive model. We'll look at some examples over here, but notice that the output of U2, those here, I'm sorry, let's go clear over here the output. This feedback has a cross feedback input over to the other dimension. So here, you're almost certainly going to use perceptual independence, and depending on the specifics, you probably will also lose perceptual separability with that kind of interaction. Also, many cases when you have this kind of interaction, you spoil both perceptual and perceptual independence and separability. But I'll show you some special cases that help your understanding and intuition where that doesn't happen. Here, just as symmetric, it's just the same kind of crosstalk. The parameters are the same in the way they affect each other. Now, those of you who have worked with Ching-Ta on systems factorial technology, especially double factorial paradigm, will certainly recognize the OR stopping rule. So if I do an experiment, and we'll see a lot of this in SFT, but it comes up here, so we might as well show how it appears in both, because we're trying to unify this part of what we're progressing in. In an OR, you would say like, well, if either of your stimuli that's the blue color, say yes, otherwise say no. Okay. That's an OR. Better yet, for one to make a contrast would be if your stimulus is either blue or a circle, say yes. And that way you really get to use both channels, right? But they don't have to be. If you have a blue triangle, instead of a blue circle, you'd still make a yes response. You could have crosstalk, again, as we talked about earlier, could be independent. We could have that stuff. You can also have the and, which hasn't been used as much, but it plays a really important role in modern use of SFT and GRT as well. Also here, the response, you say yes, if and only if it's both blue and a circle. So that's the end. And you get very different results. And many times psychologists have confounded these and expected the same results and so forth, which is quite wrong. And here's another example. I don't know if we want to, just showing how I can violate at the red level. Notice that this guy already. So notice that the shape dimension is going over and affecting the color dimension. Only the red could go to both, perturb both. In this case, it's only perturbing one. Color is not affecting the shape perception at all. Okay, so we violate perceptual separability at the red level, but not the purple level. Here's a way perceptual independence fail. Remember, if these guys are completely uncorrelated, you have perceptual independence on a certain trial, even with the same stimulus. However, here's a way that you violate perceptual independence, but you still have perceptual separability, showing they're really different concepts in a dynamic model. Okay. So if you put noise in here and you send the same noise into both channels for shape and color, you're gonna violate perceptual independence. They can't be independently correlated now. On the other hand, you're not changing the average levels or the marginal distributions for color and shape, so you still have perceptual separability.
Give us a hint, correlate. The obvious shape back. Didn't correlate.
Well, that term right there is probably a little ill-advised, but not false. But if you take regular Gaussian bars, which by definition down to the highest delta, the magnitude of the noise is independent of the noise delta cross and delta minus. Okay. So it's true Gaussian white noise. You can put that in both channels into correlation. So noise itself doesn't happen. Now, if I put in noise that was correlated, it's different noise, but it's correlated with two different noise systems in the middle of the device. You can also
One session, going on 3 to 5 develop in the brain. What could be exposed to correlated noise? It's obvious one of the outlets that shape. What kind of process, kind of neural structure generates similar inputs of like random channel?
I don't know which all this is not for me to explain, it's for you. No, seriously though, I think working with neuroscience would be important because you might find that, for example, where you get supposedly, and I don't know if you told your students about this worldwide effort testing the Miller quality of sound and vision, but there is neuroscientific evidence that there's some convergence between an auditory stimulating atmospheric awareness. And don't be there, you can noise or chance. That's a reasonable hypothesis, whether that. Yeah, and these are the, and I won't say in this because we need to move on to the actual, that's a pretty, but this is one example of the kind of thing we're talking about different ways. These systems, although linear, the postmodernists not doing any math or systems theory, or much science usually, put down linear systems, and just like they don't know anything about it. I mean, to them, linear systems are a straight line. That's not a. So, these linear systems can be quite complex, and they can explain an awful lot of stuff before, and they're always get post-form, i.e., you can write down a formula for its performance, whereas nonlinear systems almost never give you easy mathematics. We have to use numerical techniques, modern blah, 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 on and on. They're useful, but you don't need them for an incredible amount of them. Plus, you can see they're stochastic because we've got noise in them. Okay. This is, in now, we have to reassess to come up with slightly more sophisticated definitions because I'm there and when I use it, to supplement what we use accuracy. So, again, in the interest, cheating on this thing, in the interest of science, or in this case, speed, I guess, let's just go down here because, again, we don't have time to go math here. Decisional separability now on the color dimension, it's incorporates what we did when we were talking about accuracy. But it brings us new information. The probability that a certain amount of information is enough to respond red or purple gets some of the decisional criteria. Now, things operating in time, it does not depend on the amount of information about the shape, decision thresholds, or which of the four statements. So we need invariance to get this concept now. There are more things at the decision. If you have decisional separability at the advanced level, it has to satisfy all those conditions. So, of course, the conclusion for general definition theory. This is a new inference tree, so we go through and we have our tests. At the beginning, we have non-parametric tests for all these, and then we have either more particular tests using specific distribution. So, perceptual separability implies its marginal response invariance, and this is the way to prove these tests. I haven't had time to go through these, so we need another way to do that. But now we also have a speed invariance condition. There's nothing quite like that. Again, I can go into detail another time. Right, but it comes up to be a condition of stochastic. And you have, this is the marginal response invariant for probabilities. And basically, this means those distributions we saw along the axes in that figure, they're identical to one another, but that concept now also is extended to temporal. Perceptual independence now has the old report independence and the probabilities, but it also has an indicator judgment. So all of these things can be more information as well as increased acuity of the test for these important kind of psychological. characteristics. Okay, questions at that point, because now we're going to move into SSP, the information SSP. The kind of primordial systems that I would think should go back to Plato and Archimedes, if they don't, because they're the simplest kinds of systems that are at all interesting. In my early career, I showed that the very popular and still sometimes wrongly used transfer serial and parallel back in the 60s were deeply flawed. And they were flawed because why? Because I could make up and did make up mathematical models that were mathematically equivalent for the same kind of data set. The results that people thought was serial, I could produce, and that was the most important. And then I could invent mathematical limiting capacity models that were completely identical, therefore total model mimicry. That's still an incredible issue, even in math, like much less verbal modeling, is that how much can a model at different equations still might, in a certain data domain, still might mimic each other in a way that they're too close to specify. And no other field except maybe economics, I know that even a lot of math have that kind of problem. So here, of course, serial means one at a time processing, and parallel is doing them simultaneously. In the serial case, A and B can't start until A is done, so you're not just sequential. Seriality demands that non-overlapping of processing. Parallel, they start simultaneously and finish at different times and go out. And all this stuff at the end is stochastic, i.e. probabilistic. It's not deterministic. So I want to mention this. There are more complicated types of structures, architectures, you could say. Rich Schweiker, the former colleague at Purdue, really invented this approach. These kind of things come from graph theory and got employed then by engineers interested in how fast the factory can do its processes with the product, for example, going through various stations of the product out of the end. And he developed some very interesting, powerful methodology for possible architectures in the brain. And then I came along and assisted him, and we developed more stochastic. But his early stuff was like graph theory per se, it was deterministic. So when I came along at my work on was more stochastic systems, so we developed stochastic version and identification theory. And I kind of developed this idea, which I think is kind of cool. And that is that so-called, made up the name, the embellished Wheatstone Bridge. The regular Wheatstone Bridge would be the same, but it wouldn't have this extra processing. So, but let's look at what this does. I love it because it's a kind of a little cosmos, or I don't know what else to call it, passive architecture. Notice that if I'm manipulating X and Y and speed, and I'm doing this backwards, I think, to try to find out what the architecture is. Notice that this path goes through both, so it's like an embedded serial project. On the other hand, you have these processes that go through X, but not Y. I'm sorry, this is Y, but not X. This is through X, but not Y. And then what the regular Wheatstone does not have is the path that goes through neither. It's really quite a fascinating little design, kind of a compounding of almost everything that happens. In particular, it turns out that Wheatstone aspect of having both parallel and serial, and you get a completely different theory, theorems about testability and so forth, and you didn't have that in the very sure. Okay, so anyway, I and my colleagues are talking in and we think there's a lot more potential for this. Unfortunately, Schweiker has gotten up into other things, so I think that's important. And nobody's used this very much in studying cognition, so I think it's waiting to be utilized more. So we also need to talk about stopping rules. We've seen them already in the GRT context. An or decision, all that self-terminating, but self-terminating by itself is not a good term by itself because you can have minimum time stopping, so the first thing stops, or you could have so-called single self-terminating where you go through a bunch of things and you can stop whenever you find it, but that's not minimum time. So you have that, and then we have the and decision, just like core, because GRT, I don't need to talk about that very much. You may or may not have been working with Jim Paul and certain seen these guys. Before SFP came along, you could use the mean response times to argue for the existence of a serial process. But that was all. When you look for mean additivity, you'll see some more of it, but it turned out you needed deeper kinds of analyses to test parallel versus serial process. And here you see this is these guys do it. So if you have, for example, exhaustive process, i.e. you have to process both dimensions, both items, both whatever. If it's serial and you have to do both, then you get this very precise curve. You can't do positive first and then no, not right. So you get this extremely precise signatures that allow you to identify lines. If it's parallel and exhaustive, it's always, it's statistic here, is always negative. If it's minimum time, serial self-terminating, it's absolutely flat. Which is the same prediction you get in means. This is like the whole function that's provided on the zero. If it's this minimum time race kind of model and parallel, instead of a zero thing, you get this always positive. So notice how violently different that is from the universe. So we're extremely powerful, again, completely non-parametric and so-called distribution. Doesn't matter whether you got Weibull's or exponentials or gamma, and that's one thing, of course, that a lot of people criticize a lot of math sci, because it's very good math sci, but it does rely on testing to see how close a model fits the point. And as soon as you have that, well, you've got problems with this model could be more complex, even if it has the same number of parameters. That's another thing we need to teach our students more. Too often, and psychologists still think that the number of parameters identifies how complicated or complex. And that's not true. So this is just a picture to show you qualitatively different types of pattern. And that's a different kind of dimension in the architecture of parallel serial frequent, very different from what happens if you change the workload, like you increase the number of things that you have to do. Like maybe I give you 5 letters to remember instead of 1 letter. That affects, typically will affect your capacity because you're changing the workload. So let's say we're going to develop a measuring instrument or yardstick based upon the ideas of what called parallel representation or interpretation of both. So if you have a parallel system and each channel is just as good but not better than one channel, that's called a limited capacity. What many kind of active people call the race model. But they often don't have all the conditions you need for its function. If it's limited capacity, like many things found are, but then as a notice that this capacity might have been divided up and you go from one to two things, right? So you're slowing down, maybe you're getting more than after that. Now, it doesn't mean you can't have them in other systems, like on a serial model, you get quite limited, very limited. That's it. And it's very hard, in fact, for a serial model to produce unlimited, especially superflex. You notice the channels are actually getting even better when you go to two things. Where do we find that? Well, we most often find that when you've got a Gestalt situation. So your two features or dimensions or whatever may be interacting positively with each other like we saw, and that can produce supercapacitor. Here's the Plato's. Take a quick look at them for those who are mathy type. By the way, we'll notice immediately that a measure of capacity, which is based upon the mathematical interpretation of that figure you just saw, but you need to take a stopping rule and decision into account. So you can't use the same measure for an hand experiment as you do in the Morris experiment. And here's the formula using those things we saw at the very beginning of the lecture, the integrated hazard functions. The two things together, or the sum of the two things separately. It's showing that what I claimed before is that the integrated hazard function is the integrated hazard. But that can be immediately calculated or estimated in the data, taking the log of the which will. Then we get a different formula for the AND case, the sum of these things, and these are kind of so-called reverse. That's a things we don't have time to go into, but they're analogous to the regular hazard function. Okay? So, big K's are integration of the little K's. Notice that instead of the density over the survivor like here, it's the density over the community distribution. Notice a large set. Again, in that picture up there, we expect C of T to be less than 1, and that's true for either of the measures. So if it's limited, it'll be less than 1. If it stays 1 for all time, notice this is an entire function, not just one number. If it stays 1 for all time, that's unlimited. If it's greater than 1 at any point in time, it's supercapacitor. Let me go up here. So that's really important. Any questions? It's become very important for things like in human engineering, human factors, and so forth. And my colleagues here have done some of that work, and some things in connection with engineers of human factors. People also in medicine, of course, and Jim probably very good. So what we kind of mentioned a little list of things that will GRT was good for, and nothing's a thing that just for technology sells out. It's great at identifying middle architecture quite uniquely, a stopping rule that gets you installed, as in finally workload capacity. And typically, it's not anywhere close to what GRT can do on looking at dependence relationships among dimensions or features or some other kind of entity. So let's look at now at the a paradigm that actually does that, what the former slide is. So Jordan Gonzalo out of Japan and I carried out this experiment in our first paper, so-called double factorial paradigm. One factor is the load. How many things are there? Here you see 2 dots, There's one condition they were put in the eyes dichoptically, and the other they were put in both ordinary binocular. The resulting capacity were slightly different than what we're going to go into. There's both extreme evidence. And the reason, one of the reasons I've always been interested in scientific anyway, but also, it's hard to believe, but up to those years in the early 90s, seriality was still ubiquitous, i.e. everywhere. Many researchers then, and a few still now, automatically interpret reading, for example, the serial process, even though there's a lot of evidence that there's a parallel as you go down this. So I wanted to find something I used in design that was as likely as anything I could find to produce parallelism. I couldn't think of anything simpler than two dots. That's why I choose the simple stimuli. Now, in the OR paradigms, we know that if the dot is going to be right or left, you're given an affirmative yes. Only if there are no dots, then you can go. So it's a prototypical for design. And that's one of the factors, the load. Because the other factor that I should have included is Michael actually did. And now the other factor I want to vary the salient. So in a typical factorial way, and all probably see the factor design the physical or experimental. You vary something like the brightness, so how detectable it is, and therefore how speedy you are. So that's a second factor, something that's saying either the brightness, the size, or similarity. It helps you get the job done. But something you need a start, and the other thought will bear down more strongly, deeply on selective influence of how you affect these components to study the architecture and capacity. That's why it's called double factorial theory. So here's a more modern design that was introduced by Mario and his thesis. So here's where we emphasize the use of the selective input stack. Because these will all be yes. These will all be no. Some other binary. Simple. So here would be like, for example, big on the width dimension, big on the vertical dimension, here big on vertical but not width, big on width but not vertical, and little on both. So these, in terms of the yes response, the yes components are both there eventually. But if you get either one, then you can, you have to process them both. Yeah, because if you just looked at width here, you'd say no. And since the thing with the vertical, here's the vertical, yes. So that makes it a yes, but you do the process dimensions. These you can process in a self-terminated way and go through the logic for now. So anyway, that when you vary the load to here, that is here. Maybe you have absence of both. In this case, you just have no on both. And then it's the speed changes. You can get into anything. So forth and so on. So now let's talk about the selecting inputs, because that's a really critical thing. It's really critical in all of science, especially the social and biological sciences, because you're working with a black box. So we have to make assumptions in our theory and model about how outside external variables affect the internal workings. Now, Saul Sternberg, who also had the experimental design that people incorrectly interpreted as serial because it was straight reaction timeline as a function of the memory. But I was able to show that it's actually main variable there is capacity, changing the workload. And so it really didn't make much information about it. But the next thing Sternberg did 2 years later, you had this memory design, burying them in things in short-term memory and send a target and say yes. Go straight into the action. 2 years later, came up with the so-called having factors method, which is the great-grandfather, I guess, of SMP. Because he said if serial use an experimental factor to either speed up or slow down the first one and speed up or slow down the second one, we look at the so-called mean interaction contrast, like long minus long short minus the difference short long minus short short, then that should be points. Right? And powerful because it's and distribution, but it doesn't matter what the distribution says, that makes it if you have selected them. Now, he only assumed you have selected input somehow means. And it turned out when I and also the Jim-NCKU quite began to look more deeply at things like parallel processing and more complex things, it turned out that even faster or slower means. So we had to appeal to more precise characteristics of the underlying instruments in order to test see this selected. So here are the survivor functions, which we defined at the very beginning of lecture. You can do the same thing with the cumulative distribution function, but it turned out in the first prototypical or special case of the Moore paradigm that's but could use the other change time. So notice these things are beautifully ordered. So here is the longest probability it takes at least as long to finish. Notice it's the longest, dominating instead of probability. Here are the in-between ones, low and high and low. And then the fastest ones, of course, are high. So if these guys are ordered, it's not a necessary condition, but it's a sufficient condition for selected gun points open at the level we need. So this being selective at the distributional level gives you tremendously more power for investigating the dynamic. And here are the results. The exhaustive is seriality. Notice this is the earlier that I put on. This is the so-called survivor interaction contract. So it looks like what you do with the means in the Sternberg page, but now you're doing it for these entire functions. So it's not just a number, it's a whole function. And he says you get very special, unique, identifiable signatures for the different architectures and their stopping rules. So and you see also vitally, as we claimed, that both are important. You need to know the stopping rule and you need to know the architecture. Parallel OR, the minimum time race model. Down here, it's all positive. If it's parallel exhaustion, it's always negative. And it's minimum self-terminating, it's always. So a lot of people said, oh, the brain's too complex, it's never going to give you anything that's simple, but we've got, probably over 100 experiments that have been used, and it's quite rare not to get one of these really simple models. Now, I'm not saying we get more complex, and that's why it's ultimately we'll need those Wheatstone bridges and things, But at least for very simple cognition, like memory search and visual search, they're like it's all you need. So here again is a classic one. We saw that earlier, condition and so forth. Now here's a big extension. We can look at that because we wanted to extend it. So one of my former students, Nicole Terry, is one of the editors of that book. Now we bring reaction time into study capacity. So notice, for example, that this capacity is based only on reaction time, extremely useful, but you can't study speed accuracy trade-off with them, which is one of the kind of really fundamental aspects of modern fitness. It's more sort of factors. So with these measures, which we call the assessment function, they generalize the C of T or capacity topic, so we can also utilize that. Obviously, I'm going to derivations, but here's the one for end processing, the velocity processing. Here it is still the form processing. And here are some, again, we're not time to go through these, but this has been really underutilized, and one of the oldest applications of this. I guess it scares people off. It's even not done, but there have been a couple of really nice experiments. This was by Goff and Little, Dan Higgins and Bill Powell. He's one of the, probably the version of visualization of the AFT function, and we use it in pattern studies to that trade off in a really elegant way. So we talked a little about bringing reaction time into GRT. We brought now time into capacity. And another really major goal that has only recently been realized is the development of SFT, which start with the idea of no errors and use it, and it still works when you don't have really high errors. In fact, it's just an experimental and simulatory that even without its developments, SFT is quite robust. However, we also learned the general finding to actually include errors in the analysis. It's the right that we can use time in GRT to find out more about it. So, unfortunately, it's more complex in a lot of our results, but still important, I think. If processing has to be, I'll just read this. If processing has to be exhaustive, whether it's correct or error responses. Now notice that it's not a word an error or correct. The fact that it's exhaustive, which some errors have to be, it's fine. Then the SFT predictions for architecture stopping rule are identical. So this is a major, really important kind of robustness. On the other end, not so good. If things can self-terminate, like a minimum time that single target self-terminating, like we talked about, and things, then the problem is the control into the bridge is that you need to know more about how errors, because the predictions for the stopping rule and architecture things depend exactly on how errors behave. How many minutes? Well, I've been losing. I want to do a little shit. So anyway, you know, and of course that's not a defect, it's kind of a limitation. And you can kind of see the glass as half full instead of half empty, in the sense that it encourages the scientists to get more deep into the process of how the errors are made. You could have, in the extreme case, you could have a so-called yellow fast guess model where if you don't get it, you have to guess. You could have one where depends on the similarity to the tractors and things. So it does get more intricate, but it's not without its charm, and it's also forcing us to get serious about what's going on underneath it. And these are some results I want to look at. Right now, I thought I'm going to do my shake, so. Oh yeah, that's the thing. Yet another result is when there are interactions across some processes, what happens if there are interactions? And this is something I'm going to talk a lot about. Like, hey, I don't have to go through it right now, although yeah, but it's quite interesting when you dig even deeper than we have so far in the selective input. There's a number of phenomena that are quite serious, and in some ways they're kind of like some of the aspects of quantum theory, like quite. But we can talk about that today. Another thing that this is a little interesting. Another thing that we studied now about 20 years ago was studying the process of making a categorization and then a decision based on that. So like somebody comes into your 7-Eleven shop, maybe they're black or white, and categorize them, and then you got to decide whether to take an aggressive or kindly action. So that kind of idea of what's the interaction there, everybody in every mathematical model I've ever seen in any kind of scenario like this, a whole variety of fields, assumes independence of Markovian. So if it's Markovian, then your decision on whether to be aggressive or not can depend upon how you categorize it from something else. It can't depend on what your original stimulus is. Mental action law, whether you're black or white or whatever. Turns out that's not. Yeah. And again, most models still don't take that into account. We found it failed fairly majorly. Again, it didn't really fail in Markovian tendency, but far from complete. And in recent years, my colleague Jerome Bussmacher has applied his quantum theory of financial static and how interactions. So it's an important thing, and Jim-NCKU's thesis there applied SFT to that. A lot of fascinating results that we're running out of time. So yeah, this tells about the design and so forth, and you put on that. We need to DMG for which we can get it for. Get all that. So I will say that the occurrence of the interference effect that's in that design is closely associated with cognitive systems characterized by parallel neural parallel. Even though the progression of the sequential, so the parallels much more cognitively interesting than a simple series. And I'm done. I'll do my good. Okay, that's it. Thank you. Well, this has been extremely clear.
Yeah, maybe I was curious, we found a great example. If halfway on a year, how was variable, that ended up maybe equivalent to what Mario did with that logical transfer network. maybe I have to ask a question to that.
That might be,
Same like what-
I'll ask it.
Yeah.
No, but that's not, I just have a blend of what you're talking about, but yeah, that's. Question from Jim. Yes, asked Barry to come up because he came on which is the actually didn't have no fear. But this even happened before this. Has been definitely been on that. General and Schwager and Donald window work and it's kind of that. It depends on specific of the equations, if we make some revisions in travel without doing this, for something of fire, things like that. So it's a little, it's not complete, but it's achievable. It goes beyond the means of it.
Yeah, I do have one. So we have mentioned very important to frameworks. We are frameworks. So could you give us some hints how to combine these two frameworks?
How to combine them?
Yeah.
No, that's too complicated, but I should have worked up a slide. I might be able to get that in the next day or two, talking with Michael, because we've actually got some new experimental results, but I'm not sure what stage they're in. But the only thing that's published so far is doing both things with the same subjects. And it's taken a bit longer, but it's been my target for many, many years to have the same design, the same subjects, using the same trials to get information for both. A truly unified design. And that, if I give you a little hint of exactly what we would do. So you'd have something like you're varying the different features like in a GRT, but you'd also manipulate their salience and that kind of stuff. So that's the basic